Today, I'll be talking about our replication of an infrared eye tracking study using webcam eye tracking. My co-authors on this work are Sergey, Myrte, and Gillian Ramchand. We're all of the Arctic University of Norway. So first, why would we even do this? There are a number of hurdles to doing webcam eye tracking. I think anyone who does eye tracking, infrared or otherwise, knows that there's a lot of technical challenges to keep track of. The technology behind webcam eye tracking is only a few years old. It's much less precise than infrared eye tracking, both in terms of spatial resolution, so the accuracy of the gaze predictions, and in terms of temporal resolution, particularly because of the much lower and highly variable sampling rates. And then there are a lot of factors that can contribute noise to your data, making any subtle effects you're looking for harder to see. Your participant might be doing your experiment with only a bedside lamp on while downloading all 4 seasons of The Good Place and wearing tinted glasses, and you can't stop them. And beyond that, there's also the logistics. How will you program your experiment? Where will you host it? And where will you find your participants? However, there are, of course, also clear advantages. Many of us have had to shift to collecting data on the internet over the past 18 months with exciting results, as Amy's talk also demonstrated. But webcam eye tracking, I think, also has benefits outside of a pandemic. Data collection is much faster. You're able to reach a larger and potentially much more diverse pool of participants. The technology is free and thus accessible to many more researchers. And because it's open source, it makes sharing code and reproducing studies a lot easier. So before I go on, when I talk about webcam eye tracking, I'm talking about a specific piece of software called Webgazer.js, which was developed by Alexandra Paputsaki and her colleagues at Brown. It's free and open source, and it's modular, meaning that it comes with inbuilt algorithms and regression models for detecting the eyes and predicting where they're looking. But it's easy to swap those out for your own models if you have them or if you want to try something else. Webgazer was designed to track eye movements during natural web browsing behavior, but cognitive scientists quickly started to play around with it since 2016. So I've highlighted just a few studies that are relevant to this audience, but there are many more in different fields in academics. And the conclusion of these studies so far is cautiously optimistic. Results from infrared eye tracking studies generally replicate, but webcam data is noisier and effects can be expected to be smaller and appear later. So after the outbreak of COVID, several popular web-based experiment building platforms developed their own webcam eye tracking tools, which makes things a lot easier because you don't have to custom code everything yourself. Like, huge props to everybody in this cloud of papers that all wrote their own software, or most of them did. At the moment, I know that Gorilla, PC Ibex, and JSIC have their own eye tracking tools. I'm not sure about PsychoPy or any others. So our aim was to replicate a 2-alternative forced choice visual world experiment that we ran in 2019 and 20 using the new JSIC plugins for webcam eye tracking. And in doing so, we also wanted to learn more about the design considerations for these kinds of web-based eye tracking experiments. And the study we replicated was a visual world study on the incremental processing of aspect in English. And I just want to give you a quick overview of what that study looked like. This work is part of a larger cross-linguistic study on imperfective and perfective contrasts in Russian, English, and Spanish. So in the study, we were interested in whether the past progressive and simple past verb forms drew preferential looks towards snapshot of an event in an ongoing or in a completed state, respectively. Each trial consisted of a preamble, which situated the event in a narrative past, and a target sentence with the verb in either the past progressive or the simple past form. Participants had to choose which picture best matched the sentence they heard. There were 24 target trials and 24 fillers. In the fillers, participants saw pictures of 2 different events, which had the same protagonist. And to prevent a bias effect whereby hearing the auxiliary be would always uniquely predict the ongoing event picture, the filler items were constructed such that half of the items included a construction with be that described a completed event, such as grandma was successful in cracking open the nut. So we used SMI Red 500 eye tracker with integrated monitor, which was sampling at 120 Hertz. And we analyzed 66 participants. And these are the results of that study. We used cluster-based permutation analysis to identify clusters of 50 millisecond time bins where effective aspect on looking behavior is significant. So that's the shaded area on the left graph. We also ran this analysis on the simple past condition, but there was no significance, so you don't see any shading. In the top right corner, you see the offline results, so the choice of picture in each condition. There's an overwhelming preference for the ongoing event picture in the progressive condition, which is as expected. This preference is also clear to see in the left graph, where the proportion of looks towards the ongoing event picture becomes significant well before lexical verb offset. In the simple past condition, we see no significant preference for either picture in either the online or the offline results. As a side note, this raises some questions about how perfected the simple past really is, but we don't have time to get into that here. So in replicating this experiment, we hope to see both roughly the same effect size, so sort of the divergence of the two lines, and the same effect onset time. And that's a fairly fine-grained temporal resolution type thing. So that was kind of an optimistic research question for us. So how we implemented this online was that we used the new JSPsych eye tracking plugins, which were released in April of this year. And those are super user-friendly. Huge props to Josh DeLeo and Becky Gobert, who are the chief developers behind JSPsych. It was easy and fast to put together that experiment, I think. And we recruited our participants via Prolific and hosted our experiment on our university's own YATL server. Rather than recruit hundreds of people and try to filter out bad data later, we built in a few filters into the study design to exclude participants with an inadequate setup. So of the 197 people who started our study, 39 were excluded because they used the wrong equipment. Another 16 people weren't able to pass our initial calibration, in which they needed at least 50% of gaze predictions for each validation point to fall within the tolerance radius. I'm using a lot of eye tracking specific jargon here. If you have any questions about that, please fire away later. Participants got a maximum of 5 calibration attempts and received visual feedback on their performance after each attempt. And we also didn't let anyone through if they had a sampling rate of less than 5 gaze predictions per second, because we took that to be symptomatic of any number of factors that we can't really gain good insight into. Maybe internet upload and download speed is one of those. Maybe their browser just hasn't been updated or is running some sort of weird plugin or extension. We don't know, and we don't need to know. For our purposes right now, it's enough to know the sampling rate. So after the initial calibration, there were 3 recalibrations, one every 12 trials, because you see a certain amount of decay of accuracy of the calibrated Webgazer over time. So if a participant failed a recalibration, they were blocked from advancing in the experiment and given 2 pounds. This actually happened to only 8 people. The rest accidentally refreshed the web page and couldn't reload the study. We ended up with 124 participants, none of which were excluded from analysis. It was all good data. And these are the results. On the top row, you'll see the same graphs I presented earlier of the infrared version of the experiment, and on the bottom row are the results of the webcam version. We've cleaned and analyzed the data the same way in each version, and that's to say we excluded trials with over 50% track loss or gaze coordinates outside the screen dimensions. For the visualizations, we filtered out looks to neutral space, so the lines are centered around the middle of the y-axis. And as you can hopefully see, the webcam results look very similar to the infrared results. The effect size seems to be about the same, and in the progressive condition, the cluster-based permutation analysis picks out almost the same significant effect window. It just starts 50 milliseconds later. In the simple pattern of looks towards the ongoing event picture, but that also doesn't come out as significant at any point, as you can see by the lack of shading. So what's going on? Why are our data so much closer to the original than those of the earlier Webgazer studies I mentioned? There are various choices we made in our study design that may have made a modest contribution, but we think the biggest factor can be credited to Young and Krybich and Josh DeLeo, the lead developer of JSPsych. Young and Krajbic did a Webgazer replication of a neuroeconomic study and found that the temporal resolution of Webgazer dropped dramatically over the course of their pilot, which is obviously a huge problem. So they performed a kind of surgery on the Webgazer code to reduce its computational demands, which led to higher and more stable sampling rates in their main experiment. And the latest version of JSPsych includes a Webgazer script that has been similarly adapted. In our pilots using the standard Webgazer code that we did in early spring of this year, we never seemed to be able to get beyond a slower, smaller version of the effect that we saw in the infrared study. But switching to the new JSPsych toolbox was a marked improvement. And by the way, if you're using like Gorilla to run web-based experiments and now you're thinking, oh no, I've just gotten used to Gorilla, do I have to learn JSPsych now? Fear not, I've talked to a developer at Gorilla who says they're working on resolving those sampling delays in their eye tracking tools as well, and that should become available very soon. The graph just shows a distribution of our participants' mean sampling rates, which averages to a little over 20 Hertz. For visual world studies, which are mostly interested in proportions of looks towards regions of interest, I think that temporal resolution seems to be high enough. And what remains are small timing delays that vary by participant, but are more or less constant throughout the experiment. And in future work, we hope to get a better handle on those small delays so we can account for them in our data analysis. Amy already talked about this a bunch, so I won't, but there are studies out there giving a fairly detailed overview of the problems that you see in sort of getting a very precise synchronization of audio and visual stimulant onset. And that's just an open problem in running experiments in the browser using JavaScript. JavaScript as a language was just never designed to do that. So hopefully we'll see incremental improvement in that aspect of this technology over the next few years. But for our purposes here, I don't think it makes a huge difference. So in terms of spatial resolution, it's important to note that we only had to filter out about 6% of the gaze data in the infrared version, but almost 30% of the webcam data in order to get the graphs that you just saw. So that's looks to neutral space, or white space as you like. We're not entirely sure what's driving that high number of looks to neutral space. Maybe because our participants are using smaller screens, they use their peripheral vision more to perceive the pictures and are moving their eyes less. Hard to say. What we do know is that looks towards the bottom of the screen are likely to be less accurate. In several studies, beginning with the one in the bottom left by Simmelman and Weigel, 2018, you can see a tendency of the fixations to drift a bit north on the bottom row of fixation targets. And that's probably because webcams sit at the top of the screen. When you look down, your eyes become harder to track. Eyelashes and eyelids get in the way, or maybe throw shade on the rest of the eye. That's the problem with visible light spectrum cameras. And the exact problem that an infrared camera is meant to avoid. So you do always keep that problem. And as I mentioned earlier, we also know that the accuracy of the calibrated gaze prediction model degrades quite quickly over time, because no matter how obedient your participants are and how hard they try not to move their head, they will. So before we did the replication study, we ran a pilot in which we calibrated only at the start, and then we ran the whole experiment without recalibrating, and we only measured the calibration accuracy after every second trial. And you can see how quickly that precision drops off. So it was clear that we had to recalibrate, but we wanted to strike a balance between data quality and demands on our participant, because this is, demanding quite a lot, because they have to calibrate, they have to sit very still, they can't move their head at all. You're asking them to really commit to your experiment for about 20 minutes. So with every additional recalibration, you're really asking for a lot of effort. And the risk that they fail their recalibration and are kicked out of the experiment. So we ultimately chose to have only 3 recalibrations, once every 12 trials. We thought that would be enough to hike up the overall level of calibration accuracy. I would say, though, that it doesn't look like this kind of rate of decay is the same for every experiment. We ran a bunch of pilots in the early spring, as I mentioned, and we saw a slower rate of decay then. So if you're going to do something like this, I'd recommend always checking this yourself with your exact experiment design before running the study proper. just to get a sense of what you need. This is really all I'd like to leave you with today at this point, which is that right now, webcam eye tracking is precise enough for 2 picture visual world experiments. Whether it can handle more is obviously something we're all very curious to know, and that really needs to be investigated. So Mieke Slim and Rob Hartsuiker are presenting a Webgazer study with 4 pictures later today. I'm very excited for that. You should all go listen to that. I think it's the 3rd short talk session. And second, I think that as we finesse our experiment designs to account for the challenges of web-based research and the software tools continue to improve, which I absolutely expect that they will, we will achieve even better results. Lastly, I'd like to say that the tools that we use to track eye movements, program the experiment, host the study, and analyze the results are all free and open source. And I think this is awesome. It's really important in terms of making this research accessible, understandable, and reproducible. But I also think that in using and benefiting from those tools, we ought to commit to using them ethically. Eye tracking data is biometric data, and it's a hot commodity in the internet economy because tracking gaze means that you're tracking attention. So I just say that even though it may feel like our work is a long way from Silicon Valley, we need to think about what questions we're using these tools to try and answer and what the resulting knowledge can be used for. And I'd like to just end with a huge thank you to all of the developers who have contributed to making these tools available to everybody. And that includes the names that I've listed, but also a huge community of researchers and programmers who are on GitHub and just playing around and making their code available and actively contributing to making these tools better and making them available as quickly as they have become available. So shout out to them. And I look forward to taking any questions.